In this video, we'll discuss the idea of an inverse function. Essentially, this is when you want to do a function in reverse. So, given a function, um, let's just say f from a to b, two sets. The inverse function, and the notation we use for inverse function is f, so -1. This is not the same as the inverse image, so this is a dangerous notation to use, but this is the common notation. So inverse image is when we have a set and we're looking at all the things that map to elements in that set. The inverse function is a real function, so it's a it might not always exist. So let's actually say if it exists, it is the function. So it's the function that goes from B to A that essentially reverses what f does. So, yeah, it does f in reverse or backwards. So, what do I mean exactly? So specifically, it satisfies the following properties. Two properties. First one is if I do f and then f inverse, I just get back what I started with, right? So if I start in A, I go to B, and then I apply the function f inverse. That takes me back to A, and it'll do it in a predictable way. I'll just map every element back to itself. Okay, that's what I want this inverse function to do. And so it's the identity function on A. This identity function on A, the function that maps everything to itself. Okay. So that's what we would expect from an inverse function. We would also expect, and we really want both of these things to call it an inverse function, if we started in B and then applied f inverse, we're in A, that let's then apply f and go back to B. Well, what should we expect? We should expect to get back where we started with. So identity function on B, and the identity function, it's the function that that maps every element to itself. Okay, it essentially does nothing. Okay. So these are the two properties we want the inverse to satisfy. Of course, the key phrase here is if it exists. It might not exist. And let me tell you what I mean. So I'll show you what I mean. So let's say we have a function from A to B. And let's do this pictorially, actually. I think it's the easiest way to see what could go wrong. So just draw two sets, A and B. Here's A, here's B. And let's draw a few elements of A and some elements of B. And I'll use one of these arrow diagrams. So let's say we map that to that. Let's say this one is going here. And this one is going, let's just make it go to there. So this is a function here. Notice it maps every element in A to exactly one element of B. That's what we need a function to do. And the question is, can we just reverse the arrows? Well, sure, we can reverse this one, right? What about this dot here, though, right? We have a problem. So in order to find a function on B, that would need to go somewhere, but it's not coming from anywhere, right? So that's a potential problem. The other problem we can see here, if we want to reverse the arrows, well, I'd have to reverse that arrow, but wait a second, that now has me sending one element of B to two different elements of A. Again, a function can't do that. A function would need to send every element of B somewhere to exactly one element of A, right? So there are two possible issues that can arise, and they're both shown in this picture. The first one, let's explore that a little bit more. So this one, we don't know where it goes because nothing got sent to it, right? So the problem is that f is not surjective there. So note, if f is not surjective, then what's the problem? Well, there will be, I guess we can think of them as inputs of the inverse function. So there'll be things I want to view as inputs of my inverse function that don't have an output. Don't have an output, okay? So it's not going to be a function. Every input has to have an output. In fact, it has to have exactly one output. Here we didn't have exactly one output, so that's the other problem. And so the issue there is if f is not injective. See, we had two things coming into that one element. And so in order to reverse the arrows, there's some ambiguity now. Like we don't know where to send this dot back to. So if f is not injective, what would the problem be? Well, then there will be inputs. Things I'm viewing as my inputs of the new function, the inverse function, that have more than one output. Both these are problems. So if either of these comes up, we cannot define the inverse function. In fact, so we have a theorem that tells us exactly when we can define it. So we need to be surjective and injective for sure, right? Because if we're not one or the other, then we can't define the inverse function. So certainly a function would need to be bijective to have any hope of defining the inverse function. And in fact, this theorem tells us that is exactly when we can define the inverse function. So if we're given a function f from a to b, the inverse function exists if and only if f is bijective. Okay. That's the theorem. So if f is bijective, that actually guarantees that we can define the inverse function. This is enough to show that we can always define an inverse function. That's all. This is really all you need. This direction here, the forward implication, that's essentially what we talked through up here. We proved the converse. So if f is not bijective, then you have one of these two issues that prevent you from actually defining a function. And then to show this direction, how do we do that? So if f is bijective, we need to show the inverse function exists. So we would need to construct the inverse function from scratch, sort of, and then prove it has these properties. And so the idea is that, given any starting element here, which I guess is we call it y, we know that's going to be f of something. So here's my picture. And we've got x and the y. So given something here, I wanted to find a function that reverses f. But we know any element here has something that's mapped over to it. Why do we know that? Because f is surjective in particular, bijective even. But we know y is going to be f of x. And then what we can do, we know how to reverse the arrow now. So we would just define f inverse of y to be that element that mapped to y, to be x. And another issue that could potentially come up here is, how do we know that this is a well-defined element? How do we know there's not any ambiguity here? And we know that because f is injective. There's only one thing being mapped to y. So this is unambiguous. It's unambiguous since f is also injective. And why were we able to know that y is f of something? And this is because f is surjective. So using the full power of bijective here to define the inverse function. And then you would have to show that this definition satisfies both of these properties. But yeah, essentially the idea is we're literally just reversing the arrows, and we know it's unambiguous, and we know that there is actually going to be an arrow that we can reverse. So yeah, essentially both of these will follow from that. But I mean, so I went over this proof kind of a hand wavy way, but this might take up a page or so in the book to actually write out formally. But hopefully you get the idea. So a very important theorem. Now, I'm not saying that there's always going to be a formula for the inverse function. So even if there's a formula for f, there might not be a formula for the inverse function other than just saying reverse all the arrows. But often we do want to find formulas for the inverse function in practice, at least when they might exist. So we're talking about how to do that. And this is something you might have actually already seen in another math class, potentially even in high school, something like that. So finding a formula for the inverse function. How do you do that? Well, given some function, so given f from, let me call it big X to Y, just to be suggestive. Yeah, a function given by a formula f of x. Okay, so little x is in big X. That's why I call it that. We do the following. Okay. So this is some expression involving the variable x. We do the following. Let's do this in steps actually. So first we set y equal to f of x. So we let y equal f of x. I'm using as variables x and y because they commonly refer to inputs and outputs. Then what we're going to do is we're going to swap the variable names. You can do this right now or you can do it later, but I like to just do it immediately. So we're going to swap the variable names. And the idea there is the inverse function is going to reverse the inputs and outputs. So it makes sense to swap these. But I'm not doing any algebra here. I'm just literally writing x for y and y for x. So in other words, I'm just writing x equals f of y. Every place I see an x, I put a y instead. And then you actually do some algebra. So then you solve for y. Solve for y. And when you do that, you'll have a formula for the inverse function. You'll have y equal to something involving x, and that turns out is f inverse. Let's do some examples. So example, let's say we have a function from the real numbers to real numbers, given by following formula. F of x is 2x plus 5. Okay, so let's find the inverse function. Let's find a formula for the inverse function. Y is 2x plus 5, and then we literally just swap these. So just change the labels, change the names. So x equals 2y plus 5, and now I solve for y algebraically. So x minus 5 is 2y, which means that y is x minus 5 over 2. There we go. That's the formula for the inverse function. So that's f inverse of x. It's given by this formula. And notice we can actually check this. We can check that it satisfies the properties of an inverse function. Let's, I'll do one, you should try the other. Let's do f followed by f inverse. Let's see if it actually works. So f followed by f inverse. This is going to be, by definition of the composition, it's this. But yeah, what is f of x is 2x plus 5. And an f inverse of 2x plus 5. So I'm plugging in the 2x plus 5 wherever I see an x in the inverse formula. So I get 2x plus 5 minus 5 over 2. That simplifies just x. which is what we want, by the way, right? Because this is the function that just sends the input to itself, right? It's the identity. It's the function that doesn't do anything. So we want to get, the identity function is just the function f of x equals x. Okay. Let's do a trickier example. So let's do f from. By the way, I should have checked that this is surjective and injective, right? I should have checked this is actually a bijection, but it is. But that would be a good practice problem. So we prove that this is injective and surjective. That'll be a good chance to go back and review those definitions as well. So now we're going to do this function. So I'll go from r minus -1 to r. Actually, I might change this slightly. Let me set the formula first. So given by this formula, x over x plus 1. Okay, that is a function defined on all of r except for -1. So I take out that -1, right? And then I believe the range of this function is everything but 1. So I'm actually going to make this r minus 1. I'm going to make my codomain equal to the range. I'm going to restrict my codomain to that. And the reason is I really want this to be surjective. Okay, this is already injective, but I want it to be surjective. And so this is a bijection from this domain to that codomain. That means there's an inverse function. Let's find it. So y is x over x plus 1. Great. Swap x and y. So I get x is y over y plus 1. Make sure you get all the x's. And then let's come up here. Do some algebra. I have two y's. I want to solve for y. So the trick to do this, I mean, there are a couple ways to do this, but the easiest way is to multiply by the denominator. If you haven't seen this trick before, this is a good one to know. So multiply by that, and then the idea is I want to get all the y terms on one side by adding one to the other. So let's add this over to the left. So I get x is y minus xy, and here's the trick. You factor out the y, and see that makes the two y's just become one y here, and so now I can solve for it. So y is going to be x over 1 minus x. That's my inverse function. This is my f inverse. Excellent. And yes, we see that is defined on all of this set here. Okay. Let's look at a. Well, this kind of looked like a simpler example. It's actually far more complicated. So this example is actually going to be one where f inverse doesn't exist. Doesn't exist. And so the function is going to be a very familiar function. So we'll go from r to r, given by f of x is x squared. Okay. Turns out this example has a lot of subtleties. So, well, first of all, why do I say it doesn't exist, the inverse function? Well, this function is not surjective or injective, right? And we can see that by the graph of the function. It's one way to see it. You can also you can prove it finding counterexamples to the definitions of both of them. But yeah, what is our function x squared? It's a parabola. When you graph it, it's something like this. So this is, right, f of x is x squared. It's my x-axis. Here's my y-axis. And we see it's not surjective because we don't hit everything in R, right? Yeah, so this is not surjective. This is not surjective. For example, -1 is not x squared for any real number x, right? It is for a complex number, but we're going from R to R. So it's not, it's not a surjection. Surjection is a noun form for a surjective function. But it's not surjective. It's also not injective, right? And can you see that in the graph? Well, yes, that's essentially the horizontal line test. So, the horizontal line test also covers surjective. So in order for it to be injective, any horizontal line needs to meet at most 1 point, but here it meets at 2, right? And so this corresponds to the output here having 2 potential inputs, this one here and that one there. And to say every horizontal line needs to meet at least once, that's surjective. So if every horizontal line meets exactly once, then it's bijective. Okay, so anyways, we cannot invert this. So, that could be the end of the story, but turns out we still want to often do this kind of thing in reverse, right? Essentially take a square root. So let's try to define an inverse function anyway. And here's my attempt. Here's my first attempt. Let's define g to be the function. To be the function such that I have to tell you what g of something is. Let's call it g of y, just so I'm trying to make g into an inverse function of f. So I'm starting with a y. So g of y is the real number. It's defined to be the real number x such that x squared is y. Okay, I'm just trying to reverse this definition. So I'm saying, given an output to this, give me the input such that x squared is y. Okay, so here's my attempt at an inverse function. Turns out this has some issues. So there are 2 issues, maybe even more than 2. But the first issue is that g is not defined on all of R. So, for example, g of 1, we kind of went through this before. So it turns out this has to do with surjective, right? F not being surjective. So g of -1 is undefined. There is no x such that x squared equals -1. Okay. There's another problem too. So also is for a specific example, what is g of 4? Is g of 4, so the number that you square to get 4, is that 2? Or, can you think of another number? Could have been -2, right? Yeah, so 2 issues here. These are pretty big issues, but it turns out we can try to fix them. So let's fix these. So let's try to fix them. Let's try to fix these. And the first way of fixing it is this first problem. So this is a typical idea, actually. This is something we often want to do. So first, we'll actually restrict the codomain of f of x squared. Okay. We'll restrict the codomain of f to equal its range. Okay. Problem is we couldn't define g on certain numbers because those were outside of the range of f. So what if we just change this r to something else, right? And let's change it to exactly the possible inputs for g. So the range of f, in other words. So to equal its range. So we will define f from R to just the non-negative real numbers, the things that do actually have square roots. And then we'll define g from that same set. The inverse function always has to start in the exact same set, right? So that's why I really need to do this. It turns out that actually solves this first issue, right? We no longer have to worry about plugging in something that's undefined because we know this is this accounts for all the outputs of f. So we're going to get something that's already known to have a square root. The second issue is this, right? So let's try to resolve that ambiguity. Let's also say if there are two numbers, x, such that x squared equals y, we'll make g always choose the positive one. That's one way to resolve it, right? Choose the positive one. And so essentially we've defined g to be what we know to be this function, this square root. And so this is a function that actually is rather subtle. So we always define this to be the positive square root. So it's the number that when you square it to be equals y, but if there are two such numbers, we always choose the positive one. And that resolves this ambiguity of having an output here that we don't know which input to choose. So let's say we just always choose the positive one. Okay. Great. And so here's what we now have. So let's actually try this. So let's try to do g followed by f just to see if this works or not. So we'll do g first and then f. Because I think this one is actually going to work out. So let's just imagine here we're plugging in a number to g. Let's say like, well, what is this actually, right? This is take a square root of x and then square it. Do we necessarily get x back? Well, the answer is yes. As long as right, this is defined, right? So you can't plug in a negative number here, and the square root we are just declaring to always choose the positive root. So then when we square it, we actually get the number back. We can see that in an example, right? Like let's say we plug in 4, take the square root, which is 2, square that, you get 4 back. Okay. So this works. Let's check the other one. So f, then g. Okay. Now what am I doing? I am squaring first. I'm doing f, and then I'm taking the square root. Well, do we always just get x back that we started with? Unfortunately, the answer is no. So this is not an inverse still, even after we tried to fix this. So, what's an example? Well, if you plug in 2, you do 2 squared. So you got 2 squared and then the square root. That's going to be 2. But what if I plug in negative 2? See, we attempted to resolve this ambiguity, but I think I'm no longer going to be able to get negative numbers, right? Because negative 2 squared is 4. Take the square root. That's positive 2, right? Because we resolve the ambiguity, and you have to resolve the ambiguity if you even want to define a function in the first place, right? So here's what we would say, actually. This function right here is this first one is always satisfied, it turns out. You can really convince yourself. This is what's called a right inverse for f. It's a right inverse for f. When you compose it on the right of f, you always get back what you started with. Okay, so it's the second one is true. If you start in b, go backwards then forwards, you always just get the number you started with. And it turns out that as long as your function is surjective, you can always define that right inverse. So we've defined a right inverse. But notice we had to repair f to make it surjective. See, we're mapping onto, we had to change the codomain to be the entire range. So we kind of forced it to be surjective. And that didn't seem like a big change to make, right? However, f is still not injective, right? And that turns out to be the problem here, right? The f actually had two different inputs that go to the same output. And then when we try to reverse that, because this is now a function, we're always choosing the positive one. I mean, we had to make a choice one way or the other, right? You're not going to be able to get both of these inputs back, right? So this is not a left inverse. However, I know I'm going on a bit long with this example, but it's an important example. This might answer a lot of kind of lingering questions you've had, even just from algebra in the past. This is a common algebra mistake, actually, for people to say this is equal to x. It's not. It's equal to the absolute value of x, because this always takes the positive, and x could have been negative or positive, but because x squared is not injective, you're going to lose that information, right? So this is why teachers always say if you take the square root of both sides of an equation, for example, you have to add this plus or minus sign. Because if you want to cancel out the square, well, the square root function is not a true inverse for what you're doing. So if you want to keep that possible ambiguity, like you weren't sure if it's plus or minus, and you want to account for both, you have to actually add a plus or minus sign. So again, this is a very subtle example. And we're still not done because we still don't have a true inverse, right? This is not a true inverse. To really make the inverse function. So furthermore, and this is something maybe a little bit more controversial because we often don't want to do this kind of thing, but furthermore, to make f, like how could we make this injective? So to make f injective, well, we could just chop off part of the domain. We could just say, okay, if we get rid of, for example, this whole part of the domain, which is not always something you want to do, because I mean, maybe you do want to define this for negative numbers. It's perfectly well defined, right? Plugging in a negative real number. So to make f injective, we could cut off part of the domain. And this is actually something that often you do need to do if you really want to define a true inverse function. And there are two ways you can do it. You can cut off that part. You can cut off that part. You can cut off random parts of both. I wouldn't recommend that. But yeah, let's. So here's really what we're doing. We're defining f from just a positive real number, well, non-negative real numbers to the non-negative real numbers by x going to x squared, and then we're defining g again from where f left off back to where f started by x going to x square root of x. And this really is a true inverse function. So this is now both injective and surjective. So yeah. So this is g is actually an inverse function now. If you do this, if you do f followed by g, so I take a number that I know already to be positive because I'm just cutting off the negative numbers, and I square it and then take a square root. Well, then I get back to what I started with. Okay. Okay. So that's the idea, and this idea is a common one as well. Okay. You don't always want to do it, but you do have to do this if you want to define a true inverse function, something that really is a function and behaves like an inverse should. So you should be able to reverse it in both ways. And another case where you do want to do is for example, for the trig functions, for example, sine. Sine is not invertible. Sine is not invertible because well, it's not injective, it's not surjective, right? You can easily make it surjective by just limiting the codomain to the range from -1 to +1. You can't make it injective without chopping off almost everything. So, but people do this. So, and you've likely heard of it. So if you only consider the domain from -π/2 to π/2, Yes, sine is injective now, um, and surjective onto one -1 to 1, and so we can define an inverse function. So we can define the arc sine, the inverse sine, um, but it's yeah, only if we limit sine to it's a very small part of its domain. Okay, so that was enough about that. But yeah, hopefully it shows that even these simple examples that you've thought about a lot hold a lot of subtleties, and it gets even more subtle over the complex numbers, and that's because here you might think, oh, we could just choose the positive one. That seems like an obvious choice to make. Well, over the complex numbers, there's not really such a thing. I mean, complex numbers live on a plane, not a number line. So you could have two square roots on the complex plane. It's like, oh, how do I know which one to choose? They both kind of seem equally good. So it's even much more subtle still in complex analysis. But yeah, that's it for this lecture on inverse functions. Thanks for watching.